Yeah, welcome back to this afternoon session. It's a pleasure to welcome Professor Parthasarathy from Ashoka University. He'll be giving a kind of demo on playing with BFS data. So I'll tell you a little bit about how we thought of this. So while some of the organizers met, some people said BFS is making kind of some news, and it will be fantastic to kind of motivate young, upcoming, budding kind of students, kind of exciting them with if we were to show some BFS data. So that was the original thought, and I reached out to a couple of scientists from IITM Pune, Malay and Siddharth, and Professor Parthasarathy, who really was who has groomed these set of budding upcoming scientists at IIT Pune. So these three of them kindly agreed to kind of give this demo. So thank you, Professor Parthasarathy. Yeah.
Thank you.
Yeah.
Yeah, thanks. Actually, I was not supposed to come because budding scientist, budding model, it should be done by all budding people. So all the budding people could not make it here. So finally I had to rush. Okay, and then, just for a day. So what I will do, no big lecture. I mean, everybody has learned, heard many lectures from me many times. So I'll give a very brief, just 10 slides, very brief overview. Since morning we are listening, okay? We are listening. I mean, there was a question from Vishal, how do we apply some of the metrics to evaluate model? So question is, now we are going to an age where we have big data. So there is no dearth of data, whether it is observation and model. You have, terabyte order of data. But question is then what to do with this data? How to use it meaningfully, and how to make use of this data so that I can learn something and it can help me in further progress. That is the key point. Okay. So keeping that in mind, I have just collected few slides. Okay. Then we go to Achinto has, many thanks to Achinto. He has actually worked overnight, actually overtime. So he has already shared one link. I will come to that. Okay, so this is the paper is freely available. Actually, model also is free. Okay, you can go to this site and you can actually download the model, but it's not so straightforward to use it because you have to have because it is it's not a IML model, it's an NWP, number crunching. So it requires a huge supercomputer with a lot of memory, RAM, etc., etc. So, but if you have all these things, assuming, then one can actually run this model, and currently it is running 6 kilometers. You can even run it at 1 kilometer. Okay, so it can be run at any kilometer. Only thing is that you have to do all the exercises that I'm going to tell in 1 minute. So this model, in one line, it is the physics is still GFS. Okay, and the dynamical core is known as cubic octahedral. So in a minute, so this is the sequence actually. What we did is first, in the model development, so we just before lunch we saw a kind of a development process, hierarchy of model, right? So hierarchy of model, starts with 1D, then it comes to 2D, then it comes to 3D. But in 3D also there is a hierarchy. I cannot jump and start a 3D full physics model in my computer. Then I will not learn anything. Okay. So the protocol, so there is a protocol available. There is a BAMS paper in 1994 published by Held and Suarez, freely available. Read it sometime. So Held Suarez actually they have given a dynamical core without physics, easy to run. You can run it. It doesn't require HPC. Okay, you can run it in your cluster. So you should run Held Suarez in your chosen dynamical core. If you decide the icosahedral grid or whatever grid you decide, or tomorrow you come up with a new innovative, say, vertical coordinate, okay? You can do it and test it in Held-Suarez. No physics, but then run this Held-Suarez for 1 year or 2 years and see whether it is, you have the normal rotating Earth and you have all the other parameters intact. So you see whether it is producing the default waves propagations, okay? So that is, so we started this story, started from Held-Suarez. So we never ran, see, we also jumped into the, WRF directly without knowing anything. Like everyone, we did not learn anything. So this was the first learning process. Okay? So it took, if I start from alphabet, naturally, student takes a lot of time. We also took 5 years. People will laugh at us. But anyway, so Held-Suarez, the starting point. After that, preparing the grid. You prepare the icosahedral grid and put it in the globe and give some color and see how your grid looks like. So that grid was looking like this, where you have, you can see here the blue ribbon is something like 6 kilometers. And when you go towards pole, it goes to around 9 kilometers. So it gives kind of a, zooming. It gives a better resolution over tropics, less resolution over mid-latitude and so on. Okay, so after that, you run it. So so Held-Suarez gives stable, the grid is stable. Then you come to your, in this, and then you run a aquaplanet. That is the second protocol, aquaplanet. Okay, so there again you run. So, and then you add, the land, okay. And then you add orography. The moment you add orography, a lot of gravity waves, noise, okay, your model will blow up and so on and so forth. So anyway, if you survive all these stages, okay, and then you come to here where you can actually add your vegetations, okay, land cover and so on. There are also a lot of things will happen, but anyway, if you survive with all these stages, okay, and then you add all this physics stuff, okay. So what we did basically, because we cannot discover all the physics from first principle, it's not just possible. And because I was working in IITM, there is always a demand. Farmer is asking, household is asking, right? Everybody is asking better forecast. Bombay is asking, Pune is asking, Hyderabad is asking. So you have to give them, forecast. So anyway, so use GFS stuffs in this, okay? And then you finally go to your prediction, give a 10-day prediction. That's the big long story in short, this thing. So we have this, so it is currently not coupled. So it is uncoupled, okay? We are using near real-time NRSST model, data, and persist for the next 10 days. Again, there are questions you can ask, how can you persist? But, all these AGCM that are being run operationally, they are all doing that. Future will be definitely, the physics has to be improved comparable to this, grid. It has to be coupled with SST. Many of the AI stuff should go into the model. So currently this model is taking 2 hour time to produce 10-day forecast. That is, really good. When we published this paper, that time the model was taking 10 hours for 10-day forecast, okay? Yeah, so because the HPC was basically not very strong. Anyway, so yeah, now, because it's a moist convection school, right? This is one of my very favorite figure. I would ask all of you to test this in whatever model data you have, okay? And so here, one of my colleagues, she published this paper. So this is kind of an observational reanalysis. So what is plotted here is, log of precipitation here. So 0 means 1 millimeter, 1 means 10 millimeter, 2 means 100, 10 to the 2, right? So 0, 1, 2, and 0.1, okay? So it's a log of precip, okay? As isobaric level, it's a pressure level. And what you see here, contours are actually relative humidity. So basically what you have to do, is that every grid, okay, every grid for every rainfall threshold, okay, for all the levels, you have to do this, okay, and then you have to plot it. This is an excellent metric. This actually shows the convection and the moisture precipitation feedback. How? Look at this. This orange layer, okay, it means actually it is very close to 100, right? So it means, and when you are approaching from here to here, you are actually marching towards heavy rain, okay? So when you are going towards heavy rain, your moist, I mean, your boundary layer is becoming more and more and more moist. So your moist boundary layer is thickening, right? And that is giving you, so that is preconditioning and giving you deeper convection as giving you heavier rain, right? So, and then but now you come to the model. Here I have shown CFS. Here, three resolutions, 62, 126, 382 means something like, I can't remember, maybe 200, maybe 100, it's around 38, okay? Resolution for kilometers. And you see, if I don't tell you this number, it always looks similar, okay? And here you can see very prominently, you see this, there is a layer of dry layer sitting, okay, in the middle, which will try to stop your convection. And you see this gradual moisture is missing, right? It's missing here, it's missing here also, right? But what you see instead of that, when it comes to 100 millimeter per day, then your whole model levels become suddenly very moist. That's what is popcorn, okay? And it starts giving rainfall, okay? Every rain. So it is missing the boundary layer physics. It is missing the gradual margining. It is missing the, if you go back and see the diurnal, it will miss diurnal. You go back and see its diurnal cycle of convection, it will miss diurnal cycle of convection either. So it will miss everything because its physics is missing. So its moist physics is so important. So now let us see whether BFS is doing somewhat better. So this is the BFS model. This is GFS T1534, which is 12 kilometer Gaussian linear, okay? It means that it is 12 kilometer in the tropics, 12 kilometer in the North Pole, in the South Pole, all over the globe, 12.5 kilometer. This is a bias, by the way. So red means too much, blue means too less. Now you see, and this is day 1, day 3, day 5. So 120-hour forecast. You can look at this, a very prominent dry bias, okay? A prominent dry bias in the boundary layer, okay? Right from, actually it has increased, naturally error will increase with time, so, different. But then the BFS name came earlier, later. This was earlier we gave this high resolution global forecast model. So here you see the, you can see even in day 5, the line is slightly shorter, okay? Slightly less dry bias. So moisture has increased. So we have a reason to believe that this fellow, see, still positive bias is still there, intact. But at least the boundary layer, okay, seems to be, to some extent, improving than the GFS, okay? Okay, now this is one. I'm not going into more detail. Time is short. Now, this is a paper by Yasunari. You must have read 1979, Journal of Meteorological Society of Japan. Those who have not read, please read it. Without Yasunari, we cannot learn monsoon, okay? So, yeah. So, Yasunari is even before Sikka-Gadgil, mind it, okay? Sikka-Gadgil came in 1982, monthly weather review. Yasunari, 1979, okay? Only with satellite data. So what is this? He has written, I have taken from the paper directly, cloudiness fluctuation associated with northern hemisphere summer months. Okay, so basically it is he has taken a power spectra of That's why I was telling Achinta and everybody, let us take a power spectrum, okay? So see, it's very smooth because the data is very coarse, okay? But very interesting. So high frequency here and low frequency here, right? You understand, right? Day, inverse the day is the frequency, right? So 2 day, 3 day, 5 days. So you see there is a biweekly peak and there is a MGO peak, right? 30, 60 day and 10 to 20 day, right? So we get two very prominent peaks in the in this thing. So this is from observations. So you should see in any model, whether it is BFS, CFS, GFS, IFS, doesn't matter, okay? We should see, if I claim that it's a model, my model is good in monsoon, it should capture this, okay? We'll see that. Now, this, yeah, I was telling again and again, today morning also somebody, I think Vishal asked a question to Arindam, that why the, you know, the anticyclone is slightly shifted to the south. And then Arindam said, because there is a lot of rain and latent heat release. So you should tell me now that what is the friendship between this rainfall, heating, and the anticyclone? Okay. Why in tropics, always these three guys, they talk to each other, they always make a friendship, they walk alone, and then finally give us what is known as convectively coupled equatorial waves. It's a very beautiful name, right? So this is one, you know, test to see whether really in tropics they are good friend. It is indeed so. So don't look at this. This was actually from Vidyut's paper in 2011, JGR, okay? And you see what is plotted here. Don't get confused. Look at the right panel, okay? B and D, okay? So B is GPCP rainfall, okay? And 850 hectopascal wind, okay? So it is written coherent spectra, square spectra. If you don't understand coherent spectra, forget it. You just assume that I am just superimposing, you know, two power spectra. That's all, okay? So if you see, so one is contour, and you see this purple color means very, you know, high value, okay, high value of power. So you can see that there, both the coherent spectra is very high, means their friendship is very high. They are very good friend, okay? Coherent spectra is telling magnitude is very high, okay? So this is this, and then, okay, 200, 850 also is good friend, okay? See, we have compared with super parameter CAM. It's very expensive, Rolls Royce, okay? But still it could not, you know, capture. It could capture something, but not the full spectra, okay? So the problem is, why the tropics is different from exotropics is the convective coupling. Our whole story starts with convective coupling. It ends with convective coupling. Now, if my model doesn't capture convective coupling, it's not a model, okay? Now, I will not criticize AIML, but I will welcome all of you to go and test this. You will find there are a lot of work, maybe another 5 years of work needs to be done to make a AIML model focus convectively coupled and to bring this coherent spectra. Okay, now, last part. This is what is common in all CMIP model, MIP model, any model, any damn model you take. This is what is, we call it convective quasi-equilibrium, right? So the large-scale CAP tendency generation is equal to cloud scale consumption. That's what is shown here, okay? This is what we see. The color bars are different. This is from Siddharth's GRL paper. Here color bar goes up to 500, here goes up to 200, right? So here, this light blue or this red colors is range from 200 to 500. So it means the Rare 5 says the atmosphere large scale is not in equilibrium, right? The difference is very high. Whereas the model says, no, they're very much, they are following Markov-Schubert. So they are very obedient. The models are very obedient, okay? So they follow the quasi-equilibrium, okay? Atmosphere is not. So this is another bottleneck, okay, we could not overcome. And this is the reason of that bottleneck. So the large scale moisture, again, moisture monsoon school, large scale process, it will provide the moisture. Moisture will destabilize your atmosphere, large scale atmosphere. That will produce plus the generate moist convective instability that will be consumed by cloud, right? Cloud scale kinetic energy, right? My flight could not land yesterday because of this cloud scale kinetic energy diverted to Chennai, okay? And then, but then when the cloud scale kinetic energy is over, then it's warming, then the flight landed, okay? There is a large scale response. So, but the summary, take home message is, you supply more, consume more. Supply more, consume more. So the model actually is a receiver of this. More moisture instability, and more rain. More moisture instability, more rain. But then I have not discussed here another thing. Every convection scheme, they have a trigger, which is also based on relative humidity and CAPE, unfortunately. Okay, so even 500 joule per kilogram CAPE is enough to produce a lot of rain. Okay, so it doesn't even allow to build sufficient CAPE in the model. You know, there is no delay. That's why you don't get any diurnal cycle, because model is running every moment. Okay, so this is okay. Before going to collab, this is a famous paper, Segura et al. 2025. My friend Beyond Steven and all the group is he was telling that that famous kilometer scale hackathon. Okay, all the data is there. So this paper is very good. Okay, so you read it. So so now this is ICON. Okay, famous model ICON, icosidal, and this is IFS, well known, and this black line is actually the IMERGE data. Okay, now this is a mean state. This is very important. So forget about your variability, forget about your cyclone, depression, low pressure, anything. If your mean state is wrong, even if I get something correct, I shouldn't accept it. Okay, this is a mean state, and you see here what's happening is ICON is producing a completely, too strange zone of rainfall. Okay, you can see the IMERGE is going like this. It's not matching at all. IFS is at least somehow trying to, manage. So they have to work. ICON has to work. The ICON mean state is not correct. Okay, look at this. This is the latitude versus precipitation, millimeter per day. Look at this is the black one is the IMERGE, right? The green one is the IFS. Okay, and look at this ICON. The meridional rainfall belt is not correct. Okay, so I'm not telling to criticize this. What I'm telling is, don't get carried away by the wind. The moment so similar thing is BFS. We have a 6 kilometer model. Fact, India was not having any model of such kind. Correct, but then you have to work. You have to go miles away before you sleep. That famous line. Okay, now this is the last slide because AIML is a buzzing word. We just tried to see, Manmeet and Siddharth are there. So this is from our weather forecasting paper, okay? You can see IMD, GPM. All these three models could not capture these, blobs, okay? The structure of the rainfall. It happened in, this 2019, by the way, Kerala, okay? You could see the rainfall structure. But now coming to, this is forecast net and this is graphcast. You could see it is, no better than, maybe slightly better than GFS, but far away from any PA. So I cannot say this is a forecast, okay? It's not capturing anything. So this is what I think I stopped. Yeah. So now go back to your link. Achinta has already shared. All of you, did you get the link? Can you open that link? Now there are two, I mean, yeah, can it be opened here? Oh, oh, your laptop has to be connected, huh? Yeah. Okay. So this we have to disconnect or? Let this be, right? So close it? That I'm not sure they will. Oh, but we can invite them. Okay. If you could announce an AV team. An AV team? Yeah. Yeah, he's coming. So could you see the link, by the way? Anyone? I think students have received it, right? Yeah. Can you open it in Colab? Very good. And then you see there are two tasks. Okay. One is you will see that there is data. Don't download the data. It's huge. Okay. So data of OLR and rainfall from model and also from kind of observations. Did you see it? Right. And the other one is you will see the rainfall U850 and U200. Okay. From model BFS and also from I think reanalysis era 5 and from iMarch. So all these data, whether it is there in your, you get, okay, very good. So now you first do this scatter plot of Whaler and rainfall, okay, from observation. And what do you get? You let me know. If you plot the scatter plot of Whaler and the rainfall, what is coming in your screen? Anybody? Is the data accessible to everyone? Do you get the observation? So you don't have to execute anything. If you just open in Google Colab, it should plot. Is it plotting? You should, yeah, you should open with Google Colab, this one. So what they have to do now? If they have data to be cycle, not to do. No. Okay, okay. Okay, okay. So yeah, so what he's telling is if you don't want to download, I mean, you can download and do it. It is downloading will take time, right? Because a huge data is big, okay? Otherwise, you can go to this table can you check the table of contents in the left-hand side? So these are the regions, okay, we have chosen: Northeast India, Central India, Northwest India, and so on. If you go to, say, weather versus rainfall observations, over Central India, okay? Yeah. So look at this. So you can figure out, okay? So see, when the rainfall is very low, okay, lighter rainfall, okay, you see the velar is rather high, right? So it means the clouds are not so deep, right? So some kind of shallower clouds, warm cloud is producing too much of, lighter rain. But when I go towards heavier rain, okay, so these are heavier rain rates, right? You see the velar, it is coming from this band of velar, okay? But you can also argue that there are some rainfall which is coming from this low velar as well, correct? So you actually, it is not so linear that everything is coming, whatever is lighter rainfall from higher velar, whatever is heavier that is coming from the low velar. It's not exactly like that, but you could see the distribution, right? So it means that the relation broadly says that heavier rainfall comes from deeper cloud, right? Lighter rainfall comes from clouds with high velar, means warmer, right? But at the same time, you have many plots, many dots where you have rainfall not so high, but still coming from deeper cloud. So it means, so it again, it suggests, the observation itself suggests that you cannot make a deterministic regression from this, okay? It clearly suggests that you have to, I think you already attended a lecture of William Quider, okay? And this actually is a testament. It shows that your cloud, convection, and rainfall relation is not linear. It's highly nonlinear. And it basically suggests that you have to depend on some kind of a probabilistic, some kind of a stochastic approach if you want to capture these, like relations of cloud and rainfall, okay? So these are the observations, right? So can I go to, so this is Central India. If you take but you can do it for, you can take this for Western Ghat, you can take this over Northeast India and see whether this relation is working in a similar way or the, structure changes. So, yeah, now if you go to models, and then, yeah, see, this is the, so 24, 48, and 72. It's not a PPT, so I cannot put it, like side by side. But what you can very clearly see that if you remember that structure of observations, that is missing here, right? So model, you can see that even at that yeah. So you see in model, no. Battery has gone or what? Look at this. Okay. Anyway, so you see here, first of all, you see in 72 hours, okay, most of the rain is getting confined to around 200, okay? And you have lots of, most of the rains are, so it is between 0 to 200, and they are coming from all sorts of clouds, right? So one conclusion that you can draw that, this model is, working? Okay. So you see here, so this, if you compare with the observations, okay, it was like a hockey stick, right? Exponentially decreasing. But here you see most of the dots are confined in both, in all these three rainfall between 0 to 100. So it is too much of what is called, yeah, so you are getting, so this is the point. So now you try to connect the dots. So we are getting too many points between 0 to 100 mm. So it means this model is again producing too many lighter rainfall, okay? Why it is happening? Because as I said, there is no difference between GFS and BFS physics. So GFS physics is also based on, rainfall trigger is a function of Cape and relative humidity and so on. So it is triggering too many, low clouds and producing too many. So we are not getting, the structure as we get. So if I expect that I will get, so there was a paper showed Roxy and BNG's paper, right? So if I expect that, see nowadays 40 centimeter rain is very common. Every now and then Bangalore, Hyderabad, Pune, everybody is getting 40 centimeters, right? So we get very less, few dots here. So if I want to get, and this is 72 hour, means 3-day forecast. So if you want, as a forecaster, you will always like to get the forecast of heavy rain much ahead of time, not just 24 hours for taking the action, right? But see, this model, you can see very clearly, I can draw a line, okay, which will exclude very few dots beyond 40, right? So this is a problem. So this figure very clearly suggests that maybe if we have not drawn for GFS, maybe it will slightly better than GFS, but still it is producing a lot of lighter rains, okay, which is the problem of climate model. So test it. If you get access to some CMIP 7 model tomorrow, check all this. First check the mean state, what I showed, compare it with iMerge, okay? Try to reproduce that relative humidity map. It's not very difficult, it's very easy. Try to see how the moisture is behaving with the rainfall, okay, with vertical. And then plot this scatter plot, is very simple, Velar versus rainfall, and see whether all these states are consistent or not, okay? Yeah, so can we go to the next, and we have other Ian here. Can we go to Northeast? Yeah. Can we go to South India? South? Yeah. So look at this. This is, oh no, he has taken a, what is called, yeah, a box, an area of southern over southern India, okay? But you see, things are not changing much, okay? It is still, you can tell, okay, no, in 72 hours it is producing some more, but we really don't know whether it is producing due to right reason or wrong reason. So don't get excited if your model give a good result suddenly. Question it 10 times. Why it is giving? I don't know. I am finding these results for the first time today. Okay, so I don't know why it is. I mean, whether it is a noise or it is signal. I don't know. So what I'm telling is, this BFS data is now freely available. Even if it is not freely available, you also send email to director, hire him, and ask him this data. And you all students should analyze it thoroughly and come up with ideas that what is going on, whether I am getting right result due to right reason or right result due to wrong reason. Teach us, okay? It's not that we have built the model and the job is over. So what is irritating to me, I'm not very happy is that it is still producing too much of lighter rain, whether you go to southern India or central India or eastern India or whatever it is, okay? But this is a metric. So if you want to see whether the model is really producing deep cloud, you should go and check VLR and rainfall. Okay, this is a metric. Okay, now let us go to the other, we almost go to, yes, power spectrum. Yeah, so now if you go here, yes, central India, and go to the observation first. So you have 4 lines, right? Yes, see, you saw the Yasunari picture. Now this is the picture from BFS, okay? And this is the rainfall, okay? Now here the high frequency is this side, okay? Yasunari was the other way around. So this is the high frequency and this is the low frequency, 100 day, okay? What you see, because model is always noisy, it has many grid points, okay? You see there are a lot of, fluctuations, but there are some peaks you can see between, around 10 and so on. And then if you go to say around 20 to 100, you see the frequency is less noisy, okay? And see the important thing is the power is higher, right? So if you remember Yasunari's plot, there also power of the, so the point is the low frequency ISO has higher power than high frequency this biweekly mode, okay? That is why the predictability of the low frequency is higher. That's why our skill in predicting ISO is better, okay? And that's why ISO is tied up with low frequency oscillations like SST, IOD, El Nino, ENSO, what is called Eurasian snow cover, and blah, blah, blah. Every damn slow process is in tune with these slow oscillations, okay? So we get predictability, we can predict. Amplitude is high, it is easy, no? Distance start, you need a giant meter radio telescope because the amplitude is very small. But if I give you a torch, it is very easy, right? So power is high, detection is high, prediction is high, ability to prediction is high, okay? So this is the story from here. And so prediction of high frequency, heavy rain, tough, power is low, noisy, okay? And so now the question is, look at this. Now, if I remove this U850, 200 VLR precipitation, they all look same. And if he removes the color from blue, green, yellow, all if I make black, you will not be able to figure out, if I ask you, which one is 850, which one is 200, which one is VLR, you will not be able to tell, right? So this is the coupling. This is the friendship I was talking about. So your rainfall through latent heat couples the wind, okay? And wind and the vice versa, right? So that's why Arindam was telling there was too much of rain where the monsoon trough is there. So there is too much of latent heat release. So the 200 hectopascal and cyclone is slightly tilted. They are friends. They have to be tied up, okay? So this is beautiful. This is not there in extratropics, by the way. You will not get it in UK, okay? You will not get it in Germany. You have to come to tropics, okay? Yeah, can we go to now to model? Keep this in mind, huh? Now let's go to model. And so, yeah, look at this. So this is, good. Now you see, so this is precipitation, okay? And precipitation is still okay. It is showing, low frequency. It is capturing the structure. But if you come to U850, and if you try to compare with precipitations, okay, in 48 and 72, if you, I mean, it is best if you superimpose each other, okay, you will see that they are not matching. First of all, you will find that, you could see it very clearly. These peaks are missing here in U200. You will not get. So the problem is, because of its high resolution, it is still doing, it is precipitating, even though it is precipitating, it is producing lighter precipitation, but it is producing a lot of latent heat, okay? So there is some kind of coupling, but you could see very easily these peaks are missing, okay, in the model. So model is, neither, so this, what I was trying to tell, if you do, now if you go back and it is, I think, available in Python or any standard NCL, you can get a coherent spectra, squared spectra code, okay? If you get it, try to do this, okay, in any model and see whether your model is truly reproducing. This is the key. So this convective coupling is the DNA of monsoon, okay? If I cannot capture the DNA, I cannot reproduce a creature. I cannot claim that my model is doing excellently in monsoon. So you can see it very clearly. So one thing is good, that it is producing higher magnitude, higher power than the high frequency, right? So it means this model also is good in low frequency, but the purpose was different. We wanted to build this model for high frequency, right? So it is still, the power is very low, and it is not doing as good as what the observation was showing, right? And the coherence, if you see, if you just compare with precipitation to 850 to 200 here, or even if you do it here, you can very clearly see that the powers are not matching, right? So it is not, it is not coherently superimposing. It is not what is called convectively fully coupled, okay? So it is not reproducing the true characteristics of Indian summer monsoon, okay? So this is, so it means that we have to work harder. So one possible answer, I can give, that possibly coupling it with ocean may help, because ocean is the memory, right? Ocean only provides the predictability. We are still playing with a AGCM, okay, for other purpose, but I think coupling with ocean is the must, the next stage to do this model, apart from whatever physics job is remaining. So I think we're done, right? Anything else? Right? Yeah. Okay, what is this? Oh, this is Velar. Yeah, Velar also, you see, actually, we have already plotted Velar. Okay, I see Velar is too bad, actually. You see, it's completely missing the, peaks. Okay, so it is not, it's not capturing the periodicity in the convection. It's not good at all, okay? So nobody has seen it, actually. You are, first of all, today, you are the first people to see what BFS is doing in Velar and precipitation. So don't go and tell Siddharth your model is very bad. They will feel very bad. Okay, I am a person who always feel happy to get criticism. Okay, so it is good, actually. It is food for thought. It is actually the homework for the modelers. Okay, so there is no place to be complacent. There is no place to become idle. So we have to work even harder. Whatever you use, it doesn't matter. You bring AIML, you bring whatever, you improve this. Bring it to the level of Yasunari. Okay, whatever high frequency amplitude Yasunari showed, this model is not showing that. Okay, so still there are scope to reach the predictability limit. We have not yet reached the limit. So, but we are spending a lot. IITM's electric bill is 2 crore per month. Anyway, so I stop here if there is any question. Thank you, Kojinder, for the help. Any questions? So you can download, the data is there. You can download, save it to your computer, take it home, and then play it as you wish. Right?
Are there questions? Yes. Can you pass on mic?
Yeah, please, please. So do you all follow, first of all? Does it make any sense? Or you all slept? Right? Got some new idea? Or few idea? Not totally new, few? Okay, that is enough in 1 hour. Yeah, please, Sovik.
Hello, sir. I want to ask how this model differentiates between cloud and precipitation, because cloud does not guarantee precipitation always.
Sure, sure.
So in this model, how this model differentiates between cloud and precipitation?
No, the model doesn't differentiate. Model actually cooks. I mean, if you go and ask your mother, how do you differentiate water and fish? It's like that. So it is, model is a cooker, basically. Whatever ingredients I'm telling, these are all final products. So rainfall comes as a rainfall. It doesn't differentiate anything. Okay, model starts with all, geophysical fluid dynamics parameter, 7 parameters. I showed many times that equation of Bjerknes, okay, U, V, T, P, etc., etc. Then we have these conservation equations. I think these are all covered. So you have this conservation principle, right? And you have prognostic equations, right? And you have initial conditions. Charney has already told it's the initial value problem. So initial value, initially there will be no rain, right? You give U, V, T, P, RH, etc., etc. Then model starts integrating, right? And as a prediction, you will get predicted wind, predicted cloud, predicted rain. They will come as a model output. Okay? So, and how model produce rain, there are very big textbook for that. Okay? So it starts from cloud condensation nuclei, then there are various processes, okay? And then it produces rain. Okay? So it doesn't actually differentiate. There is no algorithm that it differentiates cloud like satellite or radar. It's not. It's a dynamic model. It actually produces, it generates all these parameters. Okay? That has come out as a model prediction or model output. That's what, and then we analyze whether it is CMIP 5, CMIP 6, or
maybe
BFS.
I think maybe he's also trying to ask a question that from a condensate that is suspended as a cloud.
Correct.
How is that suspension kind of distinguished from precipitation? I think that's probably is that what you
Yeah, that is.
So that is very simple. Precipitation has a very clear-cut, well-defined characteristics. So the droplet has to be of this size and this density, then only it will come as a rainfall, right? Otherwise, see this model, if you go to, or any model actually, you can see they have low cloud, they have middle cloud, they have high cloud. So those are also defined based on brightness, temperature, and all these parameters. Okay, so that way it differentiates basically.
Okay,
Yeah.
thank you.
Anything else regarding this? Moisture, convection, coupling, friendship.
I have a question.
Yes,
maybe
please.
Let's go back to the plot.
Yeah, please.
So in
This
the
plot or
observations,
the PPT you are saying?
this plot in the observations,
This
yeah.
is the co-lab actually.
Yes.
Okay.
So I was just thinking if I could bring back the observations.
Yeah, please.
BFS model, maybe. Yeah, this one. Yeah. So the question is, the plot on the right has a peak of less than 10 days in this magenta color. Yes, on the right.
Uh-huh.
And we also see a peak in outgoing long wave radiation from observations.
Yeah.
There, yes. But if we were to then compare U850 and U200,
Yeah.
there is no kind of pronounced peak as we see it in OLR and precipitation. And I was wondering, is it an, yeah,
See, no, I'll tell you. See, actually, we were discussing some time back. Professor Mike Wallace, he was visiting IIT. Okay, I asked the question. It was terrible to, analyze precipitation and weather. We don't get good skill, model performance. So he always tells, analyze 200 hectopascal velocity potential. That is a peaceful area. Okay, so you get basically what you see here. Okay, U200 or U850, they are the parameter where model produce lesser error. The moment you enter into convection, Wheeler and rainfall, models become crazy. It starts producing all sorts of nonsense and all sorts of error. That's why what you are telling, always wind field look very smooth, very perfect, okay, very suited, but not so well in Wheeler and rainfall. Okay, this is actually true. That may be getting reflected here as well. Anything else? So take this message, keep my PPT, and maybe this collab, go back and try, testing, applying in CMIP 5, in CMIP 6, and in many other models, whatever you get. In TIGI, for example, you have all forecast, 10 days forecast available freely in TIGI. You can all publish in next 6 months and send one paper. Please keep him as a co-author.
Thank you.
You will enjoy. Thank you. Thank you.
Yes,